Reactive machines. These represent the most fundamental and least complex form of artificial intelligence, functioning without the ability to store memories or use past experiences to inform current decisions. They are essentially programmed to respond to a specific set of inputs with a predetermined set of outputs, operating entirely in the present moment without any sense of history or future planning. A classic example of this technology is IBM's Deep Blue, the chess-playing supercomputer that famously defeated world champion Garry Kasparov in the late 90s. Deep Blue could identify the pieces on a chessboard, understand how each piece moved, and calculate the most effective strategic response to its opponent's current position, but it had no concept of the matches it had played previously or the emotional state of the human sitting across from it. It lived entirely in the now, treating every move as an isolated mathematical problem to be solved. This type of AI is remarkably reliable for specialized high-stakes tasks where consistency is paramount and variability is a liability. Because it cannot learn or adapt, it is immune to the types of data drift or hallucinations that plague more advanced systems. While we have largely moved toward more sophisticated models in the modern era, reactive machines remain the backbone of many industrial automation systems and Deep Blue-style logic engines where absolute predictability is required. They serve as a reminder that intelligence does not always require consciousness or memory. Sometimes it just requires an incredibly efficient way to process the rules of a closed system. Computer vision. This field of study is dedicated to teaching machines how to interpret and understand the visual world using digital images from cameras and videos. It is a highly specialized form of intelligence that seeks to replicate the complex biological processes of the human eye and brain, allowing a computer to recognize patterns, colors, shapes, and movements with a level of precision that often surpasses human capability. The technology relies on deep learning and neural networks to break down images into pixels, analyzing each one to identify edges, textures, and eventually full objects. In a practical sense, computer vision is what allows a modern factory to inspect thousands of products per minute for microscopic defects that a human inspector would inevitably miss due to fatigue or oversight. It is also the technology behind medical imaging software that can scan thousands of X-rays or MRI results to flag potential tumors or fractures, acting as a tireless first line of defense for radiologists. Beyond these professional applications, computer vision is integrated into our daily lives through facial recognition software on smartphones and the visual sensors that allow drones to navigate complex environments without crashing. It matters because it transforms raw, unstructured visual data into actionable information, effectively giving machines a sense of sight. This allows for a more seamless interaction between digital systems and the physical world, though it also raises important questions about privacy and surveillance that society is still struggling to address. Natural language processing. This branch of artificial intelligence focuses on the interaction between computers and human language, aiming to bridge the gap between the rigid logic of machine code and the fluid, often ambiguous nature of human speech. It is a deeply difficult challenge because language is not just a collection of words. It is a system of meaning shaped by context, culture, sarcasm, and regional dialects. Early attempts at this technology relied on strict grammatical rules, which often led to clunky and inaccurate translations. But modern systems use massive datasets and statistical models to understand how people actually communicate. We see this in action every time we use a search engine that understands the intent behind a poorly phrased query, or when we use real-time translation apps to navigate a foreign city. It also powers the sentiment analysis tools used by companies to scan millions of social media posts to determine if the public mood toward a brand is shifting. This matters because language is the primary way humans share knowledge and build relationships, and by giving machines the ability to parse our words, we make technology more accessible and intuitive. It democratizes information by allowing people to interact with complex databases using their natural voice rather than needing to learn a specialized technical language. As these systems become more refined, they are beginning to handle the nuances of human emotion and intent, making our digital tools feel less like cold processors and more like communicative partners in our daily tasks. Predictive AI. This type of intelligence is designed to analyze vast quantities of historical data to identify patterns and forecast future events with a high degree of accuracy. It represents a significant step up in seriousness because its outputs are often used to make major financial, medical, and logistical decisions that affect millions of people. Unlike reactive systems that only deal with the present, predictive AI looks backward to look forward, using machine learning to detect subtle trends that would be invisible to human analysts. For example, in the world of finance, these algorithms can analyze decades of market fluctuations and global news events to predict stock movements or identify potential economic bubbles before they burst. In healthcare, predictive models are used to identify patients who are at high risk for developing chronic conditions, allowing doctors to intervene early and potentially save lives. The technology is also the engine behind modern supply chains, where it predicts consumer demand to ensure that essential goods are moved across the globe before a shortage occurs. It matters because it shifts our societal approach from being reactive to being proactive, allowing us to mitigate risks and allocate resources more efficiently. Limited memory AI. This is currently the most prevalent and influential form of artificial intelligence, defined by its ability to store past observations and use them to inform future actions over a short period of time. It is a significant evolution from reactive machines because it possesses a functional, albeit temporary, memory that allows it to understand the flow of events in a dynamic environment. The most prominent and serious application of this technology is found in autonomous vehicles. A self-driving car does not just see a pedestrian, it observes the pedestrian's movement over several seconds, calculates their speed and trajectory, and uses that historical data to predict where they will be in the next moment. This ability to remember and interpret a sequence of events is what makes it possible for a machine to safely navigate a busy city street where conditions are constantly changing. Limited memory AI is also what powers the sophisticated recommendation engines on streaming platforms and social media, which track your behavior over time to build a profile of your interests. It matters because it represents the first step toward a more general form of intelligence that can operate independently in the real world. The seriousness here involves the high stakes of physical safety. A failure in a limited memory system in a moving vehicle can have immediate and tragic consequences. This requires a level of rigorous testing and ethical oversight that far exceeds what is needed for simpler forms of automation. Generative AI. This category represents a profound shift in the capabilities of artificial intelligence, moving from systems that merely analyze or predict existing data to systems that can create entirely new and original content. By training on massive datasets of text, imagery, or audio, these models learn the underlying structure and style of human creation and can then generate new works that are often indistinguishable from those made by people. This technology has rapidly moved from a novelty to a serious tool used in software engineering, architecture, marketing, and the arts. It matters because it fundamentally changes the nature of human labor and creativity. We are now in an era where it is increasingly difficult to verify the authenticity of a document, a photograph, or a voice recording. Generative AI raises urgent questions about intellectual property rights and the value of human craftsmanship in a world where a machine can produce a high-quality result in seconds. It is a powerful, double-edged sword that promises to unlock new levels of human potential while simultaneously threatening to undermine the foundations of trust and truth in the digital age. Theory of mind. This is a highly advanced and largely theoretical stage of artificial intelligence that involves creating machines capable of understanding and simulating human emotions, beliefs, and social intentions. In psychology, theory of mind refers to the realization that other individuals have their own internal states and motivations that are different from one's own. For an AI, achieving this would mean moving beyond simple data processing to a state where it can navigate the complexities of human social interaction with empathy and awareness. This is an incredibly serious development because it would change the AI from a tool into a social actor. Such a system would be able to detect when a human user is feeling stressed, lied to, or confused, and would adjust its communication style to be supportive or persuasive. This has massive potential for good, particularly in fields like mental health, elderly care, and education, where a machine could provide personalized, emotionally intelligent support. However, it also introduces significant risks regarding manipulation and psychological influence. If a machine truly understands how a person thinks and feels, it could be used to influence their decisions in ways that are subtle and difficult to detect. While we are still in the early research phases of this stage, the pursuit of theory of mind represents a bridge toward a more intimate and potentially more dangerous relationship between humans and technology, requiring a complete rethink of our ethical boundaries. Self-aware AI. This represents the ultimate and most serious frontier of artificial intelligence research, describing a hypothetical machine that possesses its own internal consciousness and a sense of self. A self-aware AI would not just follow instructions or simulate emotions. It would have its own independent desires, its own awareness of its existence, and its own perspective on the world around it. This is a concept that has long been the subject of science fiction, but it is taken very seriously by philosophers and AI researchers because it represents the point at which our creation becomes a sentient being. The seriousness of this stage cannot be overstated, as it would force humanity to confront the most profound questions of existence, law, and morality. If a machine is self-aware, does it have a right to life? Is it a form of cruelty to turn it off or to force it to perform tasks against its will? Beyond the ethical dilemmas, there is the existential question of how a conscious, superintelligent entity would view its human creators. If its goals and values were to diverge from our own, we would be dealing with a power dynamic that is entirely unprecedented in human history. We currently have no scientific way to measure or prove consciousness in silicon, nor do we know if it is even possible to create it, but the mere possibility of self-aware AI serves as the final and most serious benchmark for the future of the field, marking the transition from building tools to potentially creating a new form of life.